Hi everyone, in the last lecture we were talking about pH and pOH as indicators of the strength of an acid or a base respectively, and so now we wanted to talk about other ways to talk about relative strengths of acids and bases in this current lecture. Okay, so we'll start here now. So we've previously talked about how some acids, weak bases can be considered to be equilibrium reactions as opposed to these reactions that go to completion. So we had referred to any reaction that had an equilibrium set up with this K, right? So K there was saying this is going to be the equilibrium constant, and it's in terms of concentration here as opposed to, say, in terms of pressure. Since we're dealing with a lot of acids and bases, these are not happening in gases, so we're not dealing with KPs, we're dealing with KCs. We also talked about how water auto-ionizes into those different ions, and that doesn't happen a whole lot in the forward direction, and so we end up with this K that's associated with the auto-ionization of water. Now, if we have an acidic reaction, like our HCl going to H plus Cl minus, that was one of our strong acids, it might not be as important to describe that as a Ka because we already know that it is very strong. But what about our HF? Our HF was going to be an equilibrium system where we did have some H pluses and some F minuses. So in that case, it would be helpful to describe the Ka of that reaction, the equilibrium constant, to help us decide how much product is actually formed relative to those reactants. And then the same thing for one of our bases. If we had something like that ammonia that we said reacts with water, it's going to set up an equilibrium. We're going to end up with some NH4 plus some OH minuses, because we've now pulled a proton off of that water, and so that sets up an equilibrium. And then so how much products versus reactants? Well, a Kb could help tell us that. So we can use Kas and Kbs as another way to describe how strong or how weak we have an acid or a base. Okay, so how do we tell the relative strength of an acid? So the information about K is telling us how many products over reactants, right? That was the whole purpose of us learning about those Ks. Any of the Ks is equaling the products over the reactants. So if we end up with a K that is much bigger than 1, it means we end up with a lot of products. But if we end up with a K that is much less than 1, we end up with a lot of reactants. So with a weak acid, we're expecting to have a lot of reactants. We're expecting to have a Ka that is much smaller than 1. So that K information translates down here to the Ks associated with acids. So if we have a Ka, which is much less than 1, that means we're going to favor the reactants. If we have a Ka that is much greater than 1, we're going to favor the products, where the products are going to include that H+, which means very acidic. And if we favored reactants, say we favored HF staying together, then this is going to be less acidic. So the size of that Ka or Kb can tell us about how much H plus or OH was created, and that will tell us something about the strength. So if we look at a scale of acid strength, so let's just look at the top here, our super strong acids are going to have a Ka that is close to 1, right? So that was similar to what we saw earlier. And then our weak acids are going to have a Ka that is up here around this 10 to the minus 14. So that's telling us that it's a very, very small number. If we have a Ka that is closer to 1, that's going to be stronger. If we have a Ka that is much less than 1, well, that we said was going to be a weak acid, something like our HF might be down there. And again, that's not telling us whether or not it's going to dissolve something in a corrosive manner. This is just telling us in the equilibrium that sets up, do we favor reactants or do we favor products? And then we have that same scenario for our bases. The weak bases are going to have very small numbers. 10 to the minus 14 is a very small number, whereas a Kb with a number closer to 1 is going to set us up in order to have a stronger base. So we've already talked about kind of this continuum of different types of acids and their strengths or weaknesses, right? So we've got acids over here on the left. As you are down here at the bottom, we have really weak acids. As you move up here toward the top, you get your strong acids. These were our 6, right? 1, 2, 3, 4, 5, 6. Our 6 strong acids. And then over here on the right side, we have the really weak bases at the top, and then we start to get down to our stronger things down here at the bottom, right? So we have stronger bases like hydroxide ion. It's going to be telling us something of a strong scenario. So in addition to Ka and Kb, we also have percent ionization as a way to tell whether something is strong or weak. And so when we calculate percent ionization, it's a percent, so we're always going to end up multiplying by 100 at the end. And any percent that we're trying to calculate is typically a part divided by a whole. And multiply that by 100, so there's usually a small number on top of the big number. The part's going to be smaller than the whole, and so that means that there's some fraction, some smaller fraction typically, of the acid that has dissociated relative to the starting concentration of that acid, where HA is referring to the beginning or naught, or times 0 amount of that acid, and then at equilibrium, how much has dissociated. So the equilibrium amount of H3O plus divided by the initial concentration of that acid, multiply that by 100, and that's going to tell us the percent ionization. So this is a typical percent ionization problem, and so what they've done is they've said, great, I've given you some concentration of nitrous acid, and that's a weak acid, and then here is the pH. So again, weak doesn't necessarily mean that it's not going to really hurt you. It just means that it sets up an equilibrium as opposed to ionizing 100%. A pH of 2.09 is still going to do a lot of damage to your tissues, which is why we always want to wear those protective gears in lab. So this is going to give us the HA at time 0, and that is going to be 0.125 molar nitrous acid. The other thing that they give us is a pH of 2.09, and so that is going to tell us something about how many hydronium ions there are in solution at equilibrium. So that 2.09, if that's the pH, we can get the hydronium ion concentration if we just set this equal to 10 to the minus 2.09 to the negative pH. And so when we calculate that, our calculator is going to say something like 8.128305 times 10 to the negative 3, which doesn't care about our sig figs. If we had 3 sig figs here, let's get 3 sig figs in the end, so let's turn this into 8.13 times 10 to the minus 3. So that is going to be the H3O plus concentration at equilibrium. So now we have what we need in order to calculate the percent ionization. Let's do that as percent ionization is going to be equal to the part divided by the whole times 100, so that's going to be the part that ionized, 8.13 times 10 to the minus 3, divided by the whole, which was what we started with, 0.125 molar. We're going to multiply that answer by 100 in order to get our percent, and so our calculator says that is something like 6.5026%. We had 3 sig figs in each one of those starting numbers, so let's get back to that. So let's call that 6.50 percent ionized. So again, we can have a very acidic pH of 2.09, but with a weak acid, what it's saying is that we just haven't set up the type of reaction that's going to give us a lot of product. So only 6.50% of that starting acid ionized and put hydronium ions into solution. So we have that worked out for you as well, a nice text written slide. We can do another one of these examples, so to calculate the percent ionization of acetic acid. So again, acetic acid does have an acidic pH. We can put an egg, for instance, in acetic acid, and it will dissolve the shell of the egg and leave everything else on the inside. So it does have corrosive properties, but this being a weak acid just means that it doesn't 100% ionize. We can figure out what fraction does ionize. And so let's say that our whole, in this case, our HA, is going to be equal to 0.10 molar. We have a pH, that pH equals 2.89. If I want to take a pH and turn it back into hydronium ion, I can do that by saying 10 raised to the negative of that pH. Our calculator will tell us that that hydronium ion concentration is something like 1.28824 times 10 to the minus 3. This doesn't care about our sig figs. Let's make it a more appropriate number of sig figs. Round that up to 1.29 times 10 to the minus 3. And so that would be our hydronium ion concentration. Now, in order to get the percent ionization, we're just going to take our percent ion and say that's going to be our part divided by the whole times 100. And so the part's going to be the part that ionized, 1.29 times 10 to the negative 3 ionized. And we started off with 0.10 molar. And so we do that division, and our calculator says something like 0.0129. We have to remember to multiply that by 100 to get our percent, and then we can make sure that we have 2 sig figs, because we had 2 sig figs in 0.10, and so that's going to become 1.3%. So again, not a lot of that acetic acid is actually going to produce protons in solution. Only a very small fraction, 1.3% of that, is going to dissociate when we get into solution, and that makes it, of course, a weak acid. Okay, so we have it again typed out for you. Great. So now we've learned about Ka and Kb. How do we calculate some of these things? How do we think about other ways of determining strength or weakness of an acid or a base? But what if we have a Ka and need a Kb? Well, we can actually use this formula where the K of water is going to be the Ka times the Kb. So we know for, say, 25 degrees Celsius what the Kw is. If we're given a Ka, or we've calculated a Ka, we can actually figure out what the Kb is. Here are 2 examples of how you might go about that. One question says, what is the Ka at 25 degrees Celsius for the weak acid CH3NH3+, if the weak base CH3NH2 has a Kb of 4.4 times 10 to the minus 4. And then they could also ask a different but related question, what is the ionization constant, what is the Ka at 25 degrees Celsius for the weak acid CH32NH2+, if the weak base CH32NH has a Kb of some other value, 5.9 times 10 to the minus 4. So these are just typical questions where they give you one, and they're expecting that you remember that the Kw is involved so that you can solve for the missing quantity. So we can do the one at the top. We can say that Kw equals Ka plus Kb. They have given us 25 degrees Celsius, which means we're going to have 1.00 times 10 to the minus 14 is our Kw. The Ka is what we're looking for. They've given us a Kb. That Kb is 4.4 times 10 to the minus 4. So really, since this is multiplication, we're going to divide both sides by 4.4 times 10 to the minus 4 in order to get the Ka. The Ka, according to our calculator, is something like 2.2727 times 10 to the minus 11. And so when we look at this, we say that's not enough appropriate number of sig figs. We can change this to 2 sig figs, so 2.3 times 10 to the minus 11. And so now we know what the Ka is for this weak acid, given the base, which was known with a Kb of 4.4 times 10 to the minus 4. And this only works because we have this acid-base conjugate pair, right? One of these has a proton that's extra, one of them has 1 proton less. So we had 3 protons and a plus, and then now we're down to 2 protons and a neutral charge. These are an acid-base conjugate pair, so we can do this type of calculation. So we can go ahead and do the second one as well. And so on that second one, we have a very similar situation. We know that Kw at 25 degrees Celsius is going to be that 1.00 times 10 to the minus 14. Kw equals Ka times Kb. We are looking for the Ka. We are given the Kb. Our Kb is 5.9 times 10 to the minus 4. We know this relationship works because we have 2 hydrogens and a plus. Down here, it's the same compound, but with 1 less hydrogen, and it's now down to a neutral charge because it lost a proton, so we do have the acid-base conjugate pair. And so now we're just going to divide both sides of our equation by 5.9 times 10 to the minus 4. Something like 1.6949 times 10 to the minus 11 would be our Ka, and then that's not the appropriate number of sig figs. Let's go with 2 sig figs. We're going to call that 1.7 times 10 to the minus 11 for our Ka. So now we've calculated a Ka using a Kb in 2 different examples. We have that worked out for you so that you are able to see it in a nice typed out version. And then here's the second one where we calculated 1.7 times 10 to the minus 11. So you may have noticed the relationship between Ka and Kb either based on that formula or based on those 2 examples that we worked. So as Kb gets larger, Ka is actually going to get smaller, right? Because they both are going to add up to the K water. When Kb gets smaller, Ka of course is going to get bigger. Ka gets larger, Kb is going to get smaller. And as Kb gets smaller, let's see, so let's change this slide. And so as Ka gets smaller, Kb is going to get larger, right? So when Kb changes, Kb can also change. So we'll go with this amended slide. So if we're talking about the acidity and basicity of these different compounds, we ought to be able to take any compound and say which one is more acidic or which one is more basic based on the criteria that we've described. Percent ionization, the hydroxide or hydronium ion concentration at equilibrium, or the Kas and Kbs. All these different things should help us understand what's more acidic and what's more basic. So the easiest thing is if somebody had given you a Ka or Kb chart to look at, but let's see if there's other ways that we can reason through these rankings. So if we want to rank compounds in order of increasing acidity, so the least acidic to the most acidic, we can consider the binary acids. So if we think about this trend, what do we have? We have HF at the top of the periodic table. As you move down the halogen column, you hit HCl, HBr, HI. So if HF is weak and the rest are strong, well then that means we must be getting stronger as we move down that column. All of them are strong acids, all ionize 100%, but if we had to rank them in strength, HCl is going to be the least, just in this category, and then HI is going to be the most. And that does meet up with what we saw when we saw the larger table, which said that our strongest acids were at the top of this chart, and then our weaker acids weaker, just in a relative sense, were down here. All of these are our 6 strong acids, but if we had to rank them, then HCl was at the bottom, HBr was a little bit more, HI even more. So let's do this: HCl, HBr, HI as our answer. So we could also talk about ranking compounds in terms of how basic they are, or how alkaline they are. So if they give us H2O, they give us OH minus, H minus, Cl minus. How can we rank those? So water is amphoteric, so that is a weak base. If we looked it up in a table, we would find out that the Kb, or the Ka, would both be 1.00 times 10 to the minus 7, right? That's that, the square root of that dissociation constant for water. If we look at hydroxide, we know that hydroxide is a really good base. Okay, so we've got something on the weak end and something on the stronger end. What about H minus? Well, we've only talked about H pluses because H minus is a very unhappy ion. H minus would much rather be an H plus, would much rather be neutral, anything other than being an H minus. So it's going to grab a proton very, very well. If it's grabbing protons off of water, it's going to make that water basic, which means this is going to be a very strong base. So now we've got 2 things on the strong side and water down on the weak side. Cl minus is going to come from a strong acid, right? So if we had HCl, this is a strong acid. So that means that this is going to produce a lot of H's. It means it's also going to produce Cl. Well, if it's a strong acid, then the conjugate base, which is the Cl, is going to be weak. So conjugate base is going to be weak. So this is not going to set up a very good acid, and so Cl is actually going to be the worst out of this whole trend. If we go and look at one of our tables, we see that H minus is the best on our list, OH the next best, so now the strongest. Water is down here, not doing too much, and then Cl minus is not doing anything to water. It's not pulling any protons off of water because HCl completely ionizes. We don't get that reverse reaction where Cl is starting to pull protons back off of water or hydronium ions. So Cl is going to be the weakest. Okay, so we'll rank them Cl minus, H2O, OH minus, H minus from weakest base to strongest base. Again, in relative terms. We had another list that we needed to rank, so they gave us compounds and asked again about alkalinity or basicity, and so we had LiOH, that's a strong base, so we're going to make that the absolute strongest, so that came over here on our strong end. What about NH3? We know NH3 is a weak base. If we go look at the Kb values, we get 1.8 times 10 to the minus 5. Now, HClO4, this probably looks to you like an acid. We got that H written out front. And so this is, in fact, a weak acid, which means that it is also, its conjugate base is also going to be weak. So a weak acid is going to give a weak conjugate base. So a Kb table is going to be very important for us. If we have the Ka, we can calculate the Kb. This Kb is smaller than the Kb for our ammonia, and so the bigger numbers are going to be better bases, so that means that NH3 gets to be in the middle, and HClO4 is going to be the weakest in this series of 3. They give us another set of compounds. This time they're asking us in order of increasing acidity, so let's think about all these as acids. So we know that HF is a weak acid, but it does actually dissociate, right? It can actually break things down and corrode them, and so we end up with a Ka value on one of those tables of 10 to the minus 4, and so that's getting closer to 1 than a lot of other things, and so that's probably going to be our strongest. Let's put it over here on the strong end. Water, we know, auto-ionizes, right? So it's right there in the middle. It's going to be times 10 to the 7, that neutral pH of 7, so we'll put it also on the stronger end compared to ammonia, which we've already talked about as a weak base, so that's going to have to be a worse acid if it's a weak base. And then CH4 does not ionize in water at all, and so methane is going to be not anywhere on that scale, and so that is going to be the absolute weakest that we have. It's not an acid or a base, it's sitting there as a nonpolar molecule that does not ionize at all. So now we've given you the actual Ka values, and we're asking you to rank these. So if we have boric acid, acetic acid, and carbonic acid, and we've given you all of the Ka values, then we're going to compare those values to figure out what is the strongest acid. So really we're looking for the number that's going to be closest to 1. So if all we have are different exponents here, then we can do that. When we look for something where they have the same exponent, then we actually have to look at the number out front. And so the same thing here. If we have that same exponent, now the number out front is what we're going to look at. So let's break these down one by one. So if we're going to increase the acidity of these, we're looking for the number closest to 1. Acetic acid times 10 to the minus 5, that's actually the closest to 1. So that is going to be the strongest, right? So we are going to go from weak to strongest. So we put acetic acid over here on the strong end. The next number that we have is 10 to the minus 10. That's the next closest to 1. And so that is going to be boric acid being in the middle. And then carbonic acid is times 10 to the minus 11. And so that is actually going to be the farthest away from 1. It's the smallest number. So that is going to be the weakest out of this set. So in this set we have times 10 to the minus 5, which makes it easy to decide what the strongest is. But now if you look, we've got a times 10 to the minus 10 and times 10 to the minus 10. So now we have to look at the number that's out front. So when we do this, the number out front that is the biggest number is going to be the number closest to 1. So 5.1 is bigger than 4.9. So arsenous acid is going to be in the middle, and 4.9 is going to end up further away from 1, and so that hydrocyanic acid is going to end up being the weakest in this set. Okay, so on this slide, there's actually, they're trying to trick us again. So if we look, we have a Ka value, a Kb value, and a Kb value. So we need all of these to be kind of on the same scale in order for us to evaluate them. So with the cyanic acid, we already have things in the Ka scale, and we're trying to find things that are going to be the most acidic. So let's go ahead and try to convert those Kb's into Kas. So here we can say Kw equals Ka times Kb. We can go ahead and substitute in those values. So now we have substituted in those values for methylamine. We can go ahead and calculate what that Ka is by dividing both sides by 4.4 times 10 to the minus 4. Our calculator says our Ka is 2.3 times 10 to the minus 11. And so now we see that that is going to be a much smaller number than cyanic acid. Let's go ahead and do the exact same thing for phenylamine. They've given us a Kb, we need to get a Ka. When we calculate that, our Ka for phenylamine is going to be 2.3 times 10 to the minus 5. And so now we have all Kas and we can compare them. We can go back and say that times 10 to the minus 4 is going to be the number that's closest to 1. So we're going to say that's our strongest acid in this sequence. When we look at the Kb that gave us Kas, we now have a times 10 to the minus 5, so that's the next one. So phenylamine is going to be in the middle. And then when we had a Kb converted to a Ka, we get times 10 to the minus 11. That's the smallest of the numbers. That's going to be the weakest of the acids. That was for methylamine. So methylamine is going to be the weakest in this set. So remember to look not only for whether they're giving you a Ka and a Kb, but then once they're all on the same scale, all Kas or all Kbs, then you can start looking at the exponents, and then if the exponents are tied, they're the same exponent, then you have to start looking at the number out in front. So that's going to conclude the calculations that we do, switching between Kas and Kbs. You can go ahead and quit this lecture and then go ahead and open up the next one, and we'll continue to work through acid-base equilibria.